have another packed session coming up. As with the last section, it's going to be, moderated, and it has been organized by Abigail Calzana Diaz and also Catherine Hadler, who is the director of ESRIC. And this section is called Space to Earth. And our first speaker, I'm sure many of you know him. He has his own section outside in the foyer and online as well. You'll be able to learn all about Jim Keravela, who is from OffWorld, one of the sponsors of this event as well. So please give a very warm welcome to the effervescent, omnipresent Jim.
Good morning, everyone. Very nice to see you, and thanks to LSA, ESRIC, and the organizers for putting this together. So I'm here to tell you and give you an update about what we've done at OffWorld. Over the last 7 years, we've kind of been quiet, well, apart from me, in terms of executing effectively. And our thesis has been, from my side especially, I've always found it difficult to figure out how do we actually have a space program beyond geostationary orbit, or a space business? You can pull up the slide, a space business, when there are no customers beyond geostationary orbit facing outwards. So we decided to focus on the first planet that we could find that has aliens with bank accounts and very low launch cost, and start building our space program there. And that's what we've done. We've worked with the mining companies, terrestrial mining companies, to reimagine how we undertake mining on Earth without people present in these ridiculously dangerous environments, without using consumables, without using hydrocarbons and fuel, and without a heavy environmental impact at the surface or elsewhere with tailings and acidic runoffs and multiple other detriments that come from traditional mining. So we went from first principles, and those principles that I just outlined were actually the starting points of our optimized autonomous space programs that we had undertaken in design. And the question was, well, if you undertake the necessity of operating in space autonomously without people present and astronauts present doing mundane tasks, you bring those parameter constraints down to Earth, you have a massive CapEx and OpEx benefit, as well as an ESG and human well-being benefit to terrestrial mining, construction, infrastructure operations, and elsewhere. And so what you have here is a depiction from one of our ConOps of our robotic operations in the platinum mines. We have multiple species of robots operating in this narrow reef. And these systems are like a robotic industrial Lego kit, configurable to multiple operations, multiple tasks and systems. And here is one of our Gigabots, fully autonomous Gigabot, operating in a live platinum mine here on Earth. On this planet. We're able to undertake with this first generation system. It's a slice and dice methodology, no drill and blast, autonomous function, sensing the ore body, so it's ore body following and sensing, eliminating waste rock, zero stripping ratio, and able to continue this operation with very little downtime and continuous excavation. Now, the model is not to have one of these little puppies sitting there undertaking a mine all on its own. Get very lonely and it start having a Wall-E type complex. No, what we have is hundreds of Gigabots operating, supported by, then each one supported by several other species of robot to enable those operations to occur. And what you see here is nothing short of history. This is from some of our first campaigns last year in 2021. This is the first non-human intelligence operating in an underground mine on planet Earth, undertaking excavation with a precision, a continuity, and an environmental benefit factor that is not heard of before in the mining sector. This is precision minecrafting of the ore body, representing absolute autonomous dominance over the rock, to millimeter precision where necessary. And this allows us to have these robots continuously, laparoscopically carving into the rock like modern-day pinhole surgery. And you see the particles coming off, the packets coming off are kind of a similar size, so we can actually define the blocks that we want coming off the ore body, so that the downstream processes of other species of robots can then handle that consequently as well. So the Gigabot was the first of the species of our swarm robotic mining architecture that we've developed. It's on a modular platform that can undertake many different configurations of system. And as we improve and operate and generate more robot hours, both on the hardware side, the software layers, and the machine intelligence side, this just creates a nonlinear acceleration of capability, operational uptime, robustness, and effectiveness as we bring all those learnings into multiple ore bodies and different configurations. Then the second species we've actually deployed in pilot programs is the underground microwave mining robot. I'd say it's a generation 0.8. It's not a generation 1 just yet. It is a mobile portable system, but this was a 3-ton robot, so a heavy-duty beast that we managed to get into an underground mine as well. And this is really another revolution in the making. With our patented robotic waveguide designs, we've managed to deploy 100 megawatts of RF energy directly into the rock, disassociating the grain boundary bonds in that rock, weakening the rock, and basically with a 50 to 70% rock strength reduction, we are now turning hard rock into soft rock. The implications of doing this in the constrained rock face itself, at the ore body, is that the entire downstream processes, all the way to crushing, beneficiation, processing, and ultimate refining, have lower energetic costs, which means lower financial costs, less tool wear, less system wear, even in conventional as well as our robotic mining. And then, combined with some other factors, we are looking at over an order of magnitude cost reduction, and I'll explain what those subsequent other factors are. And so that's just a little summary of some of the things we've done so far as we've been just quietly executing. OffWorld's objectives are to ensure that we have a risk mitigator against existential catastrophe here on Earth, use the resources of outer space to improve life on Earth, both energetically and materially, and open up the frontiers so we can all get out there and start doing the stuff we want. And to get out there means to go and live and to settle. Over the last 50,000 years, we've basically migrated, evolved, moved from place to place as part of our inherent DNA. We've stopped that over the last 100 years or so. We've kind of reached the geographic frontier around planet Earth. And now it's time to open up that frontier again so that we can really move out. But the challenge with having human astronauts going out and establishing the pathways for human astronauts to go and live is the slight conundrum that human astronauts need. The right environments and conditions to live. Now we can do this as a human-to-human step function, but the real smart way for rapid growth, nonlinear growth of human civilization out into the solar system and ultimately beyond is to use robotic autonomy to the greatest extent possible, and to build those systems out as we move into cislunar space to the moon and beyond. And that means we can start building structures, we can do mining, we can do processing, and we can do all of these tasks excuse me, that we would do terrestrially in an industrial process chain. So everything we need to be able to sit in this facility here today in Luxembourg, the roads that we needed to get here, the irrigation and sewage systems that we needed to be able to survive and have water and food, and the whole supply chain, is basically the industrial model of city building. And that's what OffWorld is doing, is building a new industrial workforce that can undertake the entire gamut of end-to-end industrial processing on a modular, common layer platform for building civilization forward. But we can't just use standard Earth technologies. We do need to build new systems that can operate at scale, learning the lessons of the past, but looking at an entirely new configuration of how we undertake mining, processing, construction, manufacturing, etc. So we've developed an architecture at full stack, from the hardware modules through to the software, the intelligence layers, an operating system, with the sensory integrity to be able to operate autonomously for our terrestrial operations, and expanding that architecture and system into space operations and other domains, so that we can, excuse me, really start accelerating that development pathway. Now, the business model approach is quite unique with OffWorld. Our vision is celestial, but our business model is terrestrial. This is where the most customers exist today, so we can start here by building our entire platform terrestrially, undertake the massive iterations needed to get the thousands and thousands of robot hours, both of hardware and machine intelligence optimization. And then as we start to proceed, we can then really expand out to different sectors, such as construction, take those lessons learned, expand to lunar construction, take those lessons learned, expand to free space operations, and bring all of that, thank you so much, bring all of that into play as we integrate that IP into an ever-increasing virtuous circle that allows us to really continuously operate and optimize and maintain our platform. And you'll notice this is basically similar to a SaaS model, a software as a service model, where you have constant iteration, massive value production and generation and deployment to the customers. And we are operating a RAS model, a robotics as a service model, with our architecture. That allows us to employ the advantages of very minimal extra marginal cost for each new species of robot that we develop. So once the first species are developed and undertaking, the subsequent species of robotic development have very low marginal cost, which allow us to really develop an architecture that can reduce the cost of operations by an order of magnitude, and increase net present value for operations by multiples as well. And if you recall, this is the secret sauce of the constraining boundaries of what we need to do to develop an all-planet space program. No infrastructure, fixed infrastructure where you can help it, no humans on site doing physical labor, no environmental footprint, and no consumables. That's the ideal state, so that we can optimize and take people out of these conditions and replace them with robots that can undertake these sorts of operations. And we can reap those advantages that conventional mining is suffering from: big machines, clumsy machines, people present, slow operations, many single-point failures, to a rapid swarming disaggregated architecture for laparoscopic mining and operation. So we've been operating now for nearly 7 years. We're at the point of inflection. We're identifying land and facilities now for our first manufacturing plants, and really expanding out so that we can start, by the end of 2023, manufacturing dozens of robots per month, and then into 2024, ramp up with subsequent factories in different locations so that we can really continuously operate. The key to what we're doing is very much intelligence. Actually, OffWorld is an AI company or a machine learning company, really. We just happen to embed that intelligence in a modular robotic architecture that allows us to have a teaching system that we're developing to allow the robots to watch any human undertake any task. We bound and indicate the task parameters appropriately, and that robot can then learn without programming. And this allows us to accelerate to an unheard of level the learning pathways for different kinds of tasks and accelerate the learning to superhuman capabilities beyond the normal way a human would operate, because the robots never tire, they can be precise, and they can optimize the learning and share that learning multifold. And so we have the advantage of having a threefold intelligence learning architecture. The first, of course, is in sim, as most of us will play around when we're doing our machine learning. We generate a lot of learning algorithms in sim, but we have a very interesting interim step where we have off-world gymnasia. So gyms with research robots where we can upload any number of machine learning algorithms on different tasks of mobility, manipulation, articulation, sensing, optimization, and identification. And then we can continuously game and compare those algorithms. The third layer is that actually all of the deployments of our robots are in a continuous learning regime. So that as we deploy our robots in the field, in the mines, on construction sites, in orbit, they are constantly learning and continuously improving their operations. So that gives us a platform of collaborative, intelligent robot colonies that can undertake the tasks that we want, which minimizes drastically the pathways to subsequent sector developments. So we've been speaking with customers at airports for runway operations, for cleaning and maintenance, for road operations, because the algorithms, the architectures, and the systems beneath the tooling will basically allow us to then undertake any number of tasks. And the key to all of this to understand is that we have an urgency on planet Earth right now. We have a growing population with an increased life expectancy and standard of living, and our mining requirements are shooting up. But there is a lot of waste material out. So we need to focus on landfill mining. We need to focus on mining the debris out of the oceans. And we need to focus on mining on the lunar surface and elsewhere as we develop our architectures to allow us to really build our civilization outwards. You can see this video outside as well. It's online. OffWorld now also has two major space projects that we're working. One is a deep space constellation for robotic swarming, and the other we just got awarded was the first stage of a space debris mitigation contract, which is the first step of our in-space mining and manufacturing architecture for treating debris as salvage, space debris as salvage. That's the same problem whether it's landfills, whether it's ocean plastic and debris, or whether it's space debris. The key is to monetize the debris to turn the business operations into a salvage architecture so that we can then really start building forward and creating humanity's expansion and exodus into the solar system. So with that, thank you very much for your attention, and happy to answer any questions if there are any.
Thanks, Jim. Fascinating talk, genuinely exciting from the mining sector. We've got a couple of questions.
Yes.
The first question, you can always trust a mining person to ask about scale.
Yes.
So what is the mining rate of your current underground robots?
Fast enough to massively exceed the economic models required for significant profitability with the first generation. And the subsequent microwave and other optimization tools are going to increase those rates by multiples. I won't go into specific numbers because it won't be meaningful without context, but the deep econometric analysis has been done both by ourselves, by our customers, and by third-party independent contractors, and it's all coming out winning.
Excellent. And anything that can reduce the energy cost of comminution is
absolutely. And the one other point I would just say is we have species of robots that process, concentrate, and ultimately refine the ore in the ore body so that eventually all we'll be taking out is ingots of metal. And that will be a massive reduction of waste transportation of millions of tons, which is daft.
really exciting to hear about those plans. I had one other question on the chat, which has simply since disappeared. I think it was George Alves in the chat asked about dust, and he said from the images of those underground robots, there was some interesting dust sleeves. So how will is that what you plan for dust mitigation for lunar applications?
Yeah. So current dust mitigation we're using involves spray on the active side and certain cleaning methods for lenses and cameras on the passive side. Dust is a big problem, but we're having a lot of experience in dealing with that in increasing the robustness of the plastics, of rubbers, and of metals, and moving surfaces and close contact surfaces. So it's a constant problem to work on. Even worse on surface lunar, but eventually our robots are going to be sublunarian. So as we go deeper in, the electrostatic nature of regolith will be less of an issue, but we've got to get there first, so we have to mitigate that. Okay.
Thank you very much.
Thank you.
Thank you both so much. We have a few online talks in this section, and the next one is online. It's Miguel Olivares, actually, from the University of Luxembourg, talking about robotics. But just before we have him coming on, I must say I do notice with great fondness the lovely footwear that we have. And you can tell that Jim's from a mining world because he's brought his mining shoes on stage, I think. Anyway, let's welcome our next speaker. It's Miguel. Are you there, Miguel? Can you hear me, Miguel?
Yes, hello, I'm here.
Wonderful. We can hear you too, so it's over to you.
Okay, great. Thank you very much. So, hello everybody. I'm Miguel Olivares, the head of the Space Robotics Research Group. I'm professor on space robotics. So first of all, I would like to thank Abigail and Kathleen for organizing this session, and also ESRIC for organizing this amazing conference. Okay, so that's going to be easier after the presentation of Jean, yeah? So, of course, for space resources, we need the robot to do the job. We need the robot to boogie, yeah? So let me show you a little bit to, let's see if the clicker is working on my side. It doesn't look. Okay. Oh, yeah. So, okay, of course, we have been seeing in the presentation today and yesterday about the moon ring, we can call it. So Kathleen was showing that we expect to have a spaceport on the moon. Of course, we are always hearing things about Artemis program. And yeah, the presentation is not going smooth, but if you can click next, please. Over there. So I was mentioning that we are expecting to have a lunar base on the moon. We also consider this as a possibility to create a gas station, and for doing more and more beyond the moon, but also as a potential resort for tourists going to the moon. Yeah. So maybe if you can handle the presentation, because here it's not working well with this clicker. But please go next to the next slide. Yeah, thank you. So as Jim was mentioning, moon is tough, really, really tough. It's not good for humans. The temperatures are dropping here and there, going up and down, and the radiation is not very good for our skin and our bodies. Also for the robots are quite tricky, yeah? So next. But of course, yeah, we need to go beyond these issues with the use of robots and AI, yeah? However, the current technology is, so slow. So here are some calculations. So we consider the U22 that have a maximum speed of 200 meters per hour. The average could be around 70 meters per hour. And we know that it cannot work during the night, cannot work one day before and after the night, and also cannot work during the lunar noon. So it's just give us the U22 have a shift of 208 4 hours out of 772 hours. That means 8.5 Earth day out of the 20 Earth day that have a lunar day. Yeah, we also consider the communication delays and all the data analysis that need to be taken by the operators. We can consider that the working time, and based on the latest publication of the U22 team, that was around 4,000 hours in 2 years, and allow the U2 to go around 600 meters of traverse. Yeah, of course, if we consider this technology in order to create a lunar base, maybe we need to plan this sustainability presence of human on the moon for the 2090. Okay, but this here in a space research group at the University of Luxembourg and SNT, we are working on that. We are working on developing AI. We are working on developing different algorithms in order to make it these robots be able to boogie on the moon. Yeah. So if I am a robot, I will have some needs to know, for example, where I am, what is that, what do I need to do? So please send me the commands. How can I cache, RAS, collect, or even assembly over there? And of course, we love to work together. So who can help me? Okay, so I'm going to show you what we are doing in this research group. Please, next. Here you can see our Lunar lab. This is a lunar analog facility at the University of Luxembourg. This is around 80 square meters. And filled with 20 tons of basalt. We have also our motion capture system in order to validate our algorithms, and we modify the illumination to emulate. Okay. Something was weird here in my side. So to emulate the different illumination at the equatorial region, or at the South Pole, for example. Here on the left, you can see some of the mapping that we have been doing. Next. And also this technology allows us to participate in the ESA SBSP Space Resource Challenge. We were selected as one of the 5 teams to be on the final rounds. We are in cooperation with the Space Application Services. For sure, they should be over there. And here you can see the traverse of a small robot on more than 50 meters with all the communication issues that we have there, of course, emulating the communication issues to the moon. And also the video that was shared by ESA of the robots arriving the region of interest. Next. In addition, we need to know what is around us, yeah, and this is the purpose of this research, in where we are using machine learning approaches, to detect and identify rocks and pebbles to facilitate the remote operation and increase the level of autonomy. Because also, if you identify this rock that is different to that other rock, that allows you also to establish some landmarks in order to have a more proper localization and mapping. Next. In addition, as Jim was mentioning, yeah, this avatar methodology to control robots is really important. So currently, the teleoperation is just sending some specific waypoints commands, and that's not enough. Yeah, so we need to make it more agile. We need to make it more realistic, and therefore we are developing some AI telerobotics approaches. So, for example, we are using machine learning approach in order to identify mobility risks, to identify if the robot is getting stuck, or if it's one of or the other wheel is slippery. Yeah. So, for example, this work is in cooperation with the Satellite Communication Research Group, SITCOM, and the recent work was accepted in the Best Conference in Robotics IDOS 2022. Next. In addition, we would like to interact with the environment. So we need to grasp, collect, even assembly or mount something. So we are using reinforcement learning based approaches in order to do grasping and assembly. On the left side, you can see the training environment where the agent is learning. And on the right side, you were able to see how the real agent was able to grasp the rocks. And I have to say that here, there were directly a transfer from scene to real. So therefore, the training was done on the virtual environment, but not in the real robot, because we expect to have the robot over there. Yep. Next. In addition, we don't like to work alone, and that's also the reason that we are working on multi-robot cooperation. For doing that, as for example, Jing was mentioning, to have a lot of robots here and there, and you have been seeing the ISP, Lunar Outpost, and many other companies have the idea to have different robots on the moon. If they overcome the lunar night, that of course is a must in the future, then these robots can be used as a service, yeah. And then, of course, if we are using robots or hiring robots from other companies for doing some job, we will need to have a trustworthy operation and trust between the different companies at the operation. And therefore, we are using a blockchain-based technology in order to do more trustworthy communication, multi-robot cooperation, also data transfer, yeah, because maybe a company have already explored this specific area, and this is important for this new company that is reaching this area. So how to do the transfer without depending on the decision on Earth. This project is in collaboration with the Finatrax group, head by Gilbert Frieden at the SNP. Next. Furthermore, we have all the information gathered by the Lunar Reconnaissance Orbiter, the LRO, but this information is okay to understand how is the moon and having super beautiful pictures. But in order to operate or to increase the level of autonomy of robots, we need to have a higher resolution. Therefore, we are working on image enhancement in order to be able to create some, to develop more safety traverse planning. Next. What else? And Jing already mentioned, yeah? So space debris has space resources. There's also going to be a new next block of presentation after the launch in which you are going to have more information about that. But we are collaborating, for example, with the Space company in order to crash debris. And there's also possibilities to use it as resources. Yeah, next. In order to do this operation and to testing this operation on Earth before going to the moon, we have another lab. This is the Zero-G lab. It's a laboratory emulating on-orbit operation and services using a epoxy floor and floating platform, and in addition to robotic arm mounted in robotics rail. This lab, I'm leading this lab in collaboration with Professor Jamila from SNT Computer Vision Group. Next. And as, for example, Mensu was from Origin Space was mentioning, and we already hear this about asteroids also as a resource. On the space, we need to learn how to operate robots on very low orbits, and also do more proper landing on these specific celestial bodies. And therefore, we are in collaboration with Tohoku University with Professor Kazuya Yoshida, and developing some mobility by grasping on the surface of the moon or on the surface of an asteroid. In this case, we were using this floating platform that's using the technology developed in the research lab with air bearings, reducing the friction between the flat floor of the epoxy, made with epoxy, in order to emulate microgravity. Next. Okay, but if you find all this interesting, there is much more SNT University of Luxembourg. Next. If you are looking for our interesting master, next, please. We are offering the Interdisciplinary Spacemaster. Sorry, next. The Interdisciplinary Spacemaster, in where we can provide you the door to go to join this beautiful community, this space ecosystem at Luxembourg. Sorry, can you click next 3 times? That will be easy. Good, keep it there. Thank you. So we have this Interdisciplinary Spacemaster. This is really practical and laboratory-oriented classes where you can do your classes on the Lunar Lab, the Zero-G Lab that I just presented, but also we have the CubeSat Lab, Concurrent Design Facility, and a SATCOM Lab. So if you are interested, don't wait a second, go to isn.uni.lu and apply now. Yeah, we are still open for application for next September. However, if you are a company and you are interested on all this collaboration with my group or the research group at the SNT, so SNT have a partnership program to collaborate with industry in a very innovative, research-oriented and agile way. You can join a select group of more than 65 companies who are already working with SNT and empower your startup and company with talented researchers. Don't hesitate to contact the head of the Tech Transfer Office, Carlo Duprel, if you are interested in planetary robotics or the talks that the topics that I mentioned before. Don't hesitate to contact me directly. We have open positions for those who are more advanced on your academic career. We have a position of postdoc on smart traverse for lunar rovers, path planning with expertise on path planning or multi-robot cooperation or collaboration. We also have a position for support the Space Labs research and development specialist expert on 3D printing and or networks. Yeah. So if you are interested, don't hesitate. Apply now. You can contact me by my email. But also, I would invite you to go to visit the website of the SNT and also the stand of the SNT in order to talk with other research group people that have other position open. Yeah. Next. And finally, well, I would like to thank you all of you for attending my talk. It was absolutely a pleasure. I'm sorry not to be there, but I was doing some prospecting tasks on the moon with my buddy here, Big Hand. Also, I will be back on Earth soon, so I will be able to guide you in collaboration with my colleagues of other research group to visit the Space Lab if you are interested. So don't hesitate to come to the SNT stand tomorrow at 5:30. And then we will bring you to the labs of the SNT that are just 3 stops next to the location of the Lux Expo. So thank you very much. Yeah, let's all the robot boogie.
Thank you very much, Miguel. I couldn't see any questions online right now, but I'm sure they'll know where exactly to contact you, and if not, they'll see you tomorrow night at 5:30. So looking forward to that. Our next speaker is also online, joining us from the University of New South Wales. It's Nicholas Bennett, and the talk is entitled Lunar Propellant for the Moon and Beyond, Efficiency for Sustainability. Can you hear us, Nicholas?
Yes, I can. Thanks very much. Can you guys hear me?
Thank you, Nicholas. Over to you.
All right, that's great. Do I need to click something to make the slides come on? We're enabled. Okay, fantastic. All right, so firstly, I really appreciate the opportunity to speak with you all today. My name is Nicholas Bennett. I'm part of the Space Resources Group within the Australian Centre for Space Engineering Research at the University of New South Wales. Could I have that? Great. So my research works mainly around how to effectively and efficiently use propellant manufactured on the moon. So efficiency supports the 3 pillars of sustainability by reducing both the impact to the lunar environment and the associated social consequences, while raising economic return on investment and arguably contributing to a social good, the expansion of humanity. We focus on lunar propellant because it's a flexible product that's relatively simple to manufacture. And our propellant's inherently wasteful. We're literally moving things around on an exhaust plume. Can't be recycled or reused. So all we can do is choose logistics that reduce how much we consume to achieve an outcome. And I'll take you through some examples from our work where with lunar water, where we greatly improve efficiency and thus reduce the impact while raising the return on investment. Okay, so the plots on the top of this slide show some potential markets for propellant in cislunar space. I've shown annual volume plotted against total revenue or cost per tonne, all on log scales. And the bottom of the figure is a kind of an astrodynamic map. Now, we can use lunar propellant to raise mass up into geostationary orbit, to do active debris mitigation, and to push payloads to the moon or to the other planets. The lower left of the plot shows current and near markets, and the yellow series represents replacing European non-renewable electricity with space-based solar power stations in geostationary orbit. So there are efforts underway to get this added to Europe's 2050 net zero carbon technology roadmap. The kind of orange SpaceX Mars project would require about 700,000 tonnes of liquid oxygen in low Earth orbit annually. And the green series is for using space-based solar power to provide energy to synthesize carbon-neutral hydrocarbon fuels from CO2 in the atmosphere for hard-to-electrify applications like you know, jets and ships and things. So it's kind of like Mars ISRU on Earth. Now, the further you transport propellant from its source, the exponentially more expensive it is. And so this means that depending on the lunar propellant production cost, it could contribute anywhere from the lunar surface all the way down to low Earth orbit, with many interesting cases in highly elliptical Earth orbits like GTOs. We got a click. Yes. Now, it would be easy to assume that the projected SpaceX Starship launch costs would remove the advantage of space resources. But we adapted someone else's post-Starship off-Earth mining model and found that lunar propellant could still compete even in low Earth orbits. To fill a Starship for a Mars trip takes about 5 tankers, 10 flights of booster and tanker. So substituting lunar-sourced oxygen using similar-sized vehicles, you might require only 2 from Earth for the methane and 3 from the Moon carrying the oxygen, which is the only likely lunar propellant Starship can use. But I'll show you that this is actually a good fit for propellant derived from lunar water. Using space resources doubles the productivity of flight operations and eliminates 80% of terrestrial concerns like launch pad availability, weather holds, astrodynamically limited launch windows, airspace contention, etc. So, I mean, it looks like there can be economic advantages to lunar propellants, but are there reasons not to use them? So what the mining industry calls social license depends on environmental impact and social benefits. Now, to fill a low Earth orbit Starship using lunar deposit of mixed granular ice and regolith, we need to process about 4 football fields to a depth of 1 metre and backfill with the tailings. Now, after 5 years shipping Starships to Mars, about 2000, the tailings might just be resolvable with a backyard telescope. Now, you know, personally, I'd consider that a social benefit. It's like being able to see the pyramids and think about deep history, but here you're seeing the resources that opened up Mars and consider the deep future. Now, the amount of water present on the Moon is still a bit of an open question, and there are certainly irreplaceable science data locked up in what is there. But if you think about it, no government's going to fund gathering samples from which you can derive the chemical and isotopic makeup of millions of cubic meters of regolith. But that would just be a byproduct of many mining methods. An underground mine for a Kevin Cannon scale gigaton deposit, like an individual Great Lakes-sized deposit, would drive a Mars project for a millennia, perhaps enough time for the less unique but more challenging near-Earth and main-belt asteroids to become practical. Now, I'll illustrate the effects of logistics using some of our published work. The figure here shows an extension to a GTO orbit raising proposal that we contributed to a NASA Innovative Advanced Concept Study. Every year, about 20 tons of geostationary Earth orbit satellites are launched from Earth into geosynchronous transfer orbits. From a GTO, one needs about 1.5 kilometers a second at apogee at the top of the orbit to circularize into a geo. And we showed how to do this directly from the Moon using lunar propellant, essentially grabbing the satellite and giving it a push. And that's the orange arrow near the center of the figure. Now, to get into a LEO from the Moon, you pass through a GTO-like orbit. So to lift from LEO to GEO using lunar propellant, you've got to carry the circularization propellant and apply about 2.5 kilometers per second to get from a GTO-like orbit down to LEO, and then the same again to lift into the desired GTO, which is waste through double handling. So we used a couple of astrodynamic tricks to drop directly into the satellite's GTO and cherry pick the circularization. When we re-architected an existing LEO lift lunar proposal, we reduced the mine size by a factor of 10. Now, there's less total revenue available, but we recover more value for each ton of lunar water, and the changes increase the internal rate of return from 5% to 50%. Now, this basic ConOps is directly applicable to raising space-based solar power stations. If you apply the impulse at perigee at the bottom of the orbit rather than the top, you can push cargo to the Moon. And you can use propellant or orbital precession, where the oblate shape of the Earth twists the orientation of your orbit to reach a marshalling interplanetary vehicle or payload. If lunar propellant costs are low enough, it's worth dropping deeper into the Earth's gravity well to do distributed deliveries. You drop just enough down into LEO to lift to a higher, easy to reach orbit and repeat until you're done. It's sort of like ULA's distributed launch concept, but done over multiple different orbits. Okay, so since landing anything on the moon will always be relatively expensive, the highest value use for lunar propellant is as ascent propellant, and the next closest delivery point is low lunar orbit. However, rather than competing with propellant shipped from Earth, a propellant transport parity argument, we switch perspective to competing directly with cargo landing, a competitive parity argument. The vehicle is filled on the surface, lifts to low lunar orbit, takes on cargo and lands it. And you can see from the figures that this CONOPS eliminates double handling of vehicle mass. And the figures are to scale for mass, and I've superimposed the baseline cargo and propellant under the red CONOPS. And you can see that it lands more cargo using less propellant. It allows you to capture about double the value that you can by delivering propellant to low lunar orbit. Some secondary vehicle engineering consequences provide further benefits. You can recover about 5% more value from pure ascent propellant than it would cost to land it. Now that's not large, but profit's always at the margin. Now we expect this dynamic to extend all the way to low Earth orbit, but as you can see from the two graphs, recoverable value decays and required propellant production increases as one approaches low Earth orbit. So as lunar propellant production cost reduces, it'll become more and more economic to reach deeper and deeper into Earth's gravity well. Now, another approach to maximizing recoverable value per tonne of lunar water is to make what's usually waste into a product. So by matching lunar resources with the astrodynamics and deliverable products, you can increase usable output by up to 40%. By mass, water's 8-to-1 oxygen to hydrogen, which is electrolyzed to make 5.5 to 1 hydrolox propellant, leaving almost a third of the output as unused, often discarded oxygen. However, the hydrolox output's almost exactly what's required to take the waste oxygen to a GTO, where it's 80% of the total propellant load of a hydrolox or methalox burning vehicle. So what's often considered waste is an ideal product. You get 40% more delivered product from the same line. In the figure, I plotted a range of product and delivery orbit options. The lines smeared out from the diamonds shows the effect of increasing the oxygen burnt by the transport vehicles. The purple series are hydrogen peroxide, and you can see that the delivery into sun-synchronous orbits, perhaps for a company like OrbitFab, has good value recovery and output utilization. Now, there's a competitive landscape which will help drive improvements in the technologies. We have some other recent work that shows that one can increase the deliverable fraction of production output by packaging the propellant in expendable lunar manufactured tanks, sort of containerized propellant. So rather than push the empty containers back to the moon, one drops them off with the customer. Now, this relies on being able to manufacture metal tanks on the moon, but metals are often a likely co-product of many propellant manufacture pathways. Now, this only pays off if you can get tank manufacturing costs down to about 10% of propellant manufacturing costs, or if someone is willing to pay for the pressurized volume byproduct. So, just to sum up, some logistic patterns are much more efficient than others, and since the underlying transport and astrodynamics are not linear, what looks like a small shift can make a big difference. We don't have much choice about burning propellant, so an important component for obtaining a social license to produce lunar propellant and to making it pay is getting the most value out of the least propellant. Now, it's hard to judge the social good that's associated with expanding human activity out into the solar system, and only time will tell if the resources and our ability to exploit them will let lunar propellant play a role. But it could be that the moon is our fulcrum and lunar propellant is our lever arm. So I'll just leave it there and take questions if there are any.
Thank you so much, Nicholas. We're going to try to keep to time and move on, but there are questions coming in. Thank you, Nicholas. There are questions coming in, and I'd really like all of the speakers to just keep across the chat and to answer the questions that are coming in. I confess also myself and Catherine are not receiving all of the questions for some technical glitch within our systems. We've looked on our computers and phones, but we'll try to work on that as well. Moving on then, we have a talk here in the room from Aidan Cowley. He's our next on-site talk, so please welcome Aidan to the stage. And he's with ESA. He's going to talk about the outcomes of the ESA SBSP Workshop, the next steps and perspectives for ISRU.
Good afternoon, everyone. It's a real pleasure to be back here in Luxembourg and to see so many space resource enthusiasts in the room and to be meeting again face-to-face after such a long period of time. So today I'm presenting on behalf of a team within ESA who are working on the topic of space-based solar power. For the talk today, I'm going to give an overview for why we at ESA are now considering SBSP, or space-based solar power, for future applications. I'm going to give an overview of what SBSP is, and then I'm going to talk a little bit about some of the activities and initiatives that we're pushing forward to see if we can realize SBSP. In addition to that, I think there's a very strong synergy between space-based solar power for terrestrial uses and space-based solar power for lunar ISRU applications. And I hope by the end of this talk, we will have impressed upon you our perspective in this area. So I don't need to probably state something very obvious, but we are living in a climate emergency at the moment. As an example of this, on the 29th of April, ESA's Sentinel-3 satellite was observing the Indian subcontinent, and they saw temperatures at 7 points on the subcontinent in excess of 60 degrees centigrade. So this is a massive existential threat to us going forward in the future. And one of the key ways to address this threat, this problem for us, is resolving our energy demand, energy needs for our society, for our civilization. So, as one of the major global sources of emissions, energy is a critical part of resolving our climate crisis. And we at ESA are asking ourselves, how can we, in addition to Earth observation capabilities, use our expertise in space to help address this challenge? So, we want to ask us, how can we use space to help plug the gap in clean energy that the world needs? And we also can also look into how we can potentially use any capability we develop in that area for other use cases. And this is why we think that SBSP for terrestrial use also synergizes very strongly with SBSP for ISRU and lunar applications. We believe SBSP can represent an uninterrupted clean energy source available anywhere in the world. And this is the essence of what space-based solar power will provide. To give an overview of what SBSP is, for those of you who are not too familiar with the concept, essentially it's an orbiting satellite, a solar power satellite, which collects the incident solar radiation, itself a resource, of course. It then transmits that power back down to Earth for conversion and utilization in our energy grids here on Earth. So you can here see the schematic of an orbital power satellite, transmission of power, using power beaming technology. This could be, for example, lasers, or more conveniently, probably microwave technology, passing through the atmosphere at specific frequencies, specific spectral windows, which then gets rectified on Earth and converted into usable electricity to supply various different processes for our society. Where we see the use case for the moon is somewhat similar, and in many cases somewhat more advantageous. Again, it follows the same kind of paradigm. We are collecting incident solar radiation. We're doing so at a different location, perhaps constellations in low lunar orbit, halo orbits, or Lagrangian positions. In this case, we're using microwaves or lasers as well to provide power to a surface station on the lunar surface, where it's rectified and used to provide baseload power for ISRU processes, for example, or other processes, for example, supporting the life support needs of a habitat. And in fact, there's many really interesting technical advantages to doing SBSP on a lunar landscape, a lunar environment, as opposed to terrestrial. One big one, for example, is the absence of an atmosphere. So you don't have the issue of attenuation of the energy as it passes through an atmosphere. In terms of SBSP as a terrestrial supply, we think there's a real capability that it brings here in order of providing baseload power. So we know that renewables are going to form a large footprint in terms of how we address our energy needs in the future. But unless we radically change our energy management paradigm, we're still going to need to have baseload capability. And SBSP could represent a capability of an operation reserve or a spinning reserve baseload, where it is both continuous, reliable, and scalable in many different approaches. It also has a higher capacity factor than any other most renewable sources, so it can then provide this kind of baseload power that we still need in our society. SBSP then also has a very strong synergy with lunar ISRU, as I've already alluded to. We believe that the technologies that you would develop for SBSP for terrestrial use cases would also be enabling for lunar use cases as well. For example, the technology you need for wireless power transmission of power using SBSP satellites could also be used to enable a lot of lunar ISRU aspects, for example, prospecting rovers or construction systems or ISRU processes. And we saw a really great presentation on off-world mining earlier on about swarm robotics. Why not have a centralized hub where power is then beamed using wireless power transmission to these rovers to enable them to prospect and conduct ISRU operations? In addition, we believe that terrestrial SBSP could become an eventual major driver for both lunar and cislunar industrial development. At the end of the day, when you talk about economics regarding space resources, at the bottom of every economic pyramid is the energy question. And SBSP can be that capability of powering up these ISRU processes at scale. And additionally, lunar ISRU could become an enabler of sustainable SBSP in the future. SBSP could well become one of the customers for many of the lunar ISRU products we're talking about. So we were all familiar with consumables, commodities like lunar oxygen, propellant, even ISRU construction materials. It could be in the future that the SBSP becomes the user of these products in order to enable them to become, in order to build more and more of these SBSP satellites in orbit, for example. So then, moving on to what we as ESA are doing at the moment in terms of trying to promote and develop SBSP concepts going forward. Last summer, we had a very successful OSIP, Open Space Innovation Platform campaign on clean energy, where we were looking for new ideas around solar power from space. And this led to a number of studies being issued on topics that I think if you look at very quickly, you'll see have a very strong synergy between many ISRU aspects. So for example, we're looking into solar power satellite concepts for lunar power, so providing that base load power that you would need to support ISRU activities. Looking into photovoltaic technology, looking into power conversion technologies, wireless power transmission, which I've already talked about, and even topics like in-space manufacturing and assembly, which obviously can very heavily benefit from lunar ISRU activities. In addition to that, we had a very successful workshop in December of last year, and this workshop brought together key stakeholders and key experts in the area of SBSP and related technologies. And some of the major outputs from this workshop are presented here. And the really interesting thing is that we found that space-based solar power is technically feasible. We believe it's scalable, affordable, and accessible. And it's something that we should, while there's still many technical challenges around realizing, they're not game stoppers, they're not showstoppers. So we're not talking about something that's 50 or 60 years away in the future. We're talking about something that could be realized relatively soon. And in fact, there are many initiatives across the world where SBSP technologies are now already being demonstrated in orbit, and many more are being planned in the near future. We believe that a demonstration power station by 2040 is a reasonable prospect. While it will require a number of near-term steps to realize, we do not believe these are beyond the capabilities or technical innovation. As I already mentioned and hope to impress upon you, we also believe that space-based solar power can have a very strong initial use case for powering lunar exploration, enabling lunar ISRU capabilities. And lastly, one of the last points that I want to dwell on as well is we also believe that SBSP would also require the development of new launch capabilities, larger launch capacities, and this would have obviously a very significant knock-on effect for developing other ISRU processes and products in the future, where mass is still a constraining factor. So going forward, we have a kind of an internal roadmap that we're trying to work on in ESA to develop SBSP. We're trying to elicit support and interest around the concept of SBSP to try to initiate some preparatory program and activities within the agency, and also to do some ground demonstration of this technology so that we can actually show that this does work and that the technology has advanced since the last time these things have been studied in depth. We'd like to see then perhaps towards the end of this decade a demonstration of a small subscale demonstrator in space, and moving on then towards a medium scale demonstrator and a larger, hopefully in the future then by 2040, a gigawatt scale space-based solar power station with meaningful provision of power into our terrestrial grid and also potentially lunar applications as well. So to conclude, and just to remark upon something that I heard yesterday from the talks of our Director General and also the Minister for the Economy of Luxembourg yesterday, they talked about the space economy. They talked about space as an economic location. I think it's very worthwhile to remember that at the base of every economic pyramid is the provision of energy. And for all our processes that we're investigating here as space resource enthusiasts, energy is a critical component. And I believe that space solar power is a tool we can use to help realize Lunar ISRU and other applications. So I hope we've impressed upon you today this perspective. And just to conclude then, on behalf of my colleagues in ESA, who are very motivated and very active in this area, thank you for your attention this afternoon. And if you have any questions, you can catch me now or you can catch me during the rest of this week. Thank you for your attention.
Thanks, Aidan. A really fascinating subject that we'll surely hear lots more about into the future. I know there's a lot of support within ESA. You won't be surprised to hear that Angeliki left a message saying space-based solar power for the win. But we do have a question from David Carl, who says, thanks, Aidan, very exciting stuff. So SBSP for Lunar ISRU. Is the argument for using it on the moon not also an argument for using solar panels directly on the surface of the moon because of the lack of the atmosphere? What would be better? Why would we use SBSP compared to solar panels?
It's a very good and very real question. I think the advantages of using SBSP is you could perhaps approach a paradigm like we have here on Earth. So at the moment we have distributed energy grids that basically move power from a centralized power station to where it's needed. By realizing an SBSP satellite in Lunar to power Lunar ISRU, you could essentially have one or a multiple of SBSP satellites providing power to a number of stations on the moon. Rather than having bespoke energy solutions for each location, you can essentially beam it to these locations and have a centralized location. So there's obviously a trade-off to be done there depending on what kind of process you are. But also in terms of capacity, SBSP, when it realizes its full-scale gigawatt demonstration, this would be a significant amount of power, probably more than you could realize for each individual ISRU process on the moon. So we think it would scale much better when you approach it from a SBSP type approach.
Great, thank you very much.
Thank you.
There, thanks very much, Aidan. Our next talk and the final one of this Space to Earth section is online again. It's Alex Ellery, who is joining us and from Carleton University. The talk is entitled Strategies for Sustainable LRU. Can you hear us, Alex?
Yeah, can you hear me?
Yes, we can. Over to you.
Okay, thank you. I'm just waiting for my slides to come up. Oh, okay, great, okay. I'd like to discuss the issue of sustainability as it applies to ISRU on the moon. Now, this necessarily requires a long-term perspective, but I believe we can gaze into the crystal ball because the unfolding of any kind of lunar industrialization process will follow a logical and predictable path. Next slide, please. Thank you. Now, we must assume that it is desirable to maximize self-sufficiency by reducing reliance on an Earth-based supply chain. Now, this is often erroneously described as sustainability, but what it actually means is actually to minimize financial cost of lunar exploration. Now, sustainability requires that the consumption of finite in situ resources should not be depleted for future generations. Now, it is crucial to address this now, as decisions we take today will have legacy effects on future lunar capacities. Now, one of the assumptions I make is that the lunar infrastructure will be developed as an evolving moon village as a model. Now, quite apart from lunar bases and all its paraphernalia, this would necessarily involve production machines that process lunar resources into stuff. Now, my starting point for stuff to be made is a common or garden Earth orbiting spacecraft. Now, an Earth orbiting spacecraft has a set of well-established subsystems with average fractional allocations to the total spacecraft dry mass. Now, this is not as restrictive as it sounds, because we can adapt this to this breakdown to suit variations on the theme. So, for instance, if we want to build a lunar base, we know that there are no propulsive aspects, but the mass will be dominated by regolith-derived structures. Similarly, if we look at a chemical processing facility, this will require extensive power systems, primarily thermal, and a heavy reliance on refractory ceramics, but it still requires things like structure, thermal control systems, power, and so on. Next slide, please. So looking more closely at the subsystem breakdown, avionics may be a constant fraction across different lunar platforms for bases, rovers, launchers, etc. Similarly, regarding the wiring harness and tensile structures and so on, we have similar constant factors. But the moon does exhibit a 2-week day-night cycle with heavy implications for both power systems and thermal control regimes. We can start to drill down to specifics of each subsystem to build our demandite. Now, demandite is the ideal mix of materials required to construct our model spacecraft. Next slide, please. This is our demandite. Now, this constitutes the predictable path of ISRU. On the left columns, we see the desired functionality required of materials to implement different subsystem functions. We've also quantified it according to our spacecraft model. And on the right-hand side, we have candidate lunar-derived materials that can execute those functions. And the key to minimizing the materials inventory is the multifunctionality of many materials. So, for example, lunar anorthite is a source of aluminium metal, alumina ceramic, silica ceramic, fused silica glass, quartz, alloying silicon in silicon steel and silumint, and quicklime. Aluminium itself is also multifunctional. It can be employed for tensile structures, thermal conduction straps, thermal radiators, optical reflectors, electrical wiring, potentiometer-based sensing, alnico magnets, and thermite welding. Next slide, please. So I apologize at the outset about this slide, but I wanted to fit a lunar industrial ecology into this slide. Now, this ecology converts in situ minerals on the left through a handful of processes into specific functional entities listed on the right. Now, in the middle of that table, we see lunar anorthite that is converted using HCl leaching supplied as an earth-sourced reagent that is not consumed into various components we require. In effect, we're using an artificial form of chemical weathering. We have other lunar minerals here, ilmenite, olivine, nickeline, meteoritic material, volatiles, etc. All these processes are interlinked so that the waste of one feeds into another as feedstock to minimize waste, and reagents such as HCl are recycled. Next slide, please. So with the lunar industrial ecology, we have the opportunity to design in a rational approach to lunar industrialization. We have the opportunity to impose sustainability through recycling, unlike how we do things on Earth. We have grown on Earth, our industry has grown according to economic drivers that basically degrade our biosphere. We do not have to repeat the mistakes of the past. So rather than bringing our bad habits with us, let us design our lunar activities to be rational and sustainable. And there are a couple of interesting observations. If we feed our lunar industrial ecology into magma electrolysis or the metalysis FFC process, we obtain a bow tie architecture in which a large number of inputs feed into a small number of processes, which then output into a wide diversity of products. Now, the bow tie architecture is characteristic of biological metabolism. So this suggests that we might apply bio-inspired approaches that are known to be adaptable, robust, and resilient. For example, genetic regulatory networks may be implemented to coordinate different processes of the lunar industrial ecology. Next slide, please. So with this long-term view in mind, we suggest that we should minimize lunar water resources that we mine for burning as propellant and oxidizer. Now, future generations of lunar settlers require water for other purposes. Even with recycling, there will be some losses. Now, if we look at the Mars exploration reference architecture, it requires 568 tons of liquid hydrogen and oxygen, excluding the surface landing and ascent component. The launch from the lunar surface to the gateway, for example, requires a further 1,295 tons of the same. But we can eliminate this using electromagnetic launches powered by renewable solar energy stored in flywheels. We can supply liquid oxygen from lunar minerals, reducing the lunar supply requirement to 81 tons of liquid hydrogen. And this is 4% of our original total. So this is sustainability through husbandry. I believe we should be exercising these approaches as we develop a lunar infrastructure, rather than squandering our finite water resources that are available on the moon. In the long term, as the lunar moon village grows, so will its demand for resources. So let's not fall into the economist think trap, in which is glibly assumed that future generations will solve problems that we create for them. And I'll leave it there. Thank you for listening.
Thank you so much.
No questions?
I'm sure there are questions. We haven't seen any coming in yet, but if you're online, you can address all of the questions and direct your answers to the individual people as well in the chat function, on the computer, in the forum function, on the app.
Sure.
Thank you so much.
Okay.
And thank you for your time coming to us from Canada. We hope everything is good over there for you.
Thank you.
Thank you, and hopefully you can stay with us for the next section as well. So that ends the sections that were organised by Abigail Calzana Diaz and also Catherine Hadler. Thank you again to those for organising 3 sessions actually. So to Abigail and Catherine, thank you so much.